Okay, next we're going to talk about linked lists. Okay, so we know a little bit about arrays. Arrays are just one way to group a collection of data all of the same type. So you've seen me draw this picture many, many times. Right, an array, or a vector, or a safe array. It's just this collection of items where we have a single name, and then we access items using the name, some array notation, and an offset. However, there are some issues with arrays that we're probably aware of. The size of an array is fixed, right? And it's pretty expensive to change the size. We have learned about how to change the size of an array using a dynamic array. But creating a new one and copying all the values over, that's a pretty expensive operation. Another problem with arrays is you have to stay in bounds of the array. So no exception gets thrown when you go outside the bounds of the array. In fact, nothing happens at all when you go outside the bounds of the array, except you might step on somebody else's data. And arrays don't know their own size. So you end up hard-coding array size in all your loops, which is moderately annoying because if you change the size, you have to go and remember to change all those loops. Arrays are very nice, though, in that it's easy to declare them, and we get random access to all the elements in the array. So it takes the exact same amount of time to grab this piece of data, the first, as it does the last. Okay. Now, we're going to talk about this thing called a linked list, which is an unordered collection, just like an array is, of data of all the same type, but it's structured differently than an array. So a linked list looks something like this. A linked list is different from an array because the elements are not necessarily next to each other in memory. That was actually a requirement of an array, and that's how we get our random access, is all the items in the array had to be right next to each other. With the linked list, that's not true. And in fact, when the linked list grows, the new items are not necessarily put next to each other. So if we look at these 5 items, right, they might be spread throughout memory like this. So these are those pieces of data. Okay, so we think of a list as a series of nodes that are linked together with pointers. So the this value right here, that might represent this node, and this one points to the next one, which who knows, it might even be behind it here. And then this one points to a next one, that might be here, and this one points to the next one, that might be here, and this one points to the next one. Okay. So we see in memory all these different pieces of data. They're spread out, and they have these links that link them together. So a node is a combination of data to be stored in the list and a link to the next node. Okay. So when we talk about a node, there's a piece of data, and then there's a link to the next one. We can traverse a list by following the link from one node to the next. Now the physical order of the nodes in memory is different from the traversal order. And by traverse I just mean, kind of go through each one of the items in the linked list and do something with them. In order to traverse a linked list, we need to be able to access the very first element of the list. And there's a special link that's not part of any node that we call the head. Okay, so the head is a pointer to the very first node. Okay. And the very last node in a linked list should indicate that there are no more nodes beyond it. So each one of these nodes has a pointer that points somewhere. The very last node in a linked list, its pointer should be set to null. Okay. So all nodes will be created on the heap, and the links will be pointers to nodes. And then to traverse the linked list, one starts at the head and continues to follow the links until a null pointer is reached. Right, so if I wanted to march through these different elements, I would say, all right, let's find the head. The head points to the first item. We'll do something with it, and then we'll follow the link to the next one. We'll do something with that piece of data and follow the link to the next one. And then here we'll see that the link is null. It's a null pointer. So we know we've processed all the elements in the linked list. Okay, so what is the public interface to our linked list? What is that going to look like? Okay, well, our linked list is going to be a templated class. So we have template class T. This particular version I'm calling my linked list. And we have a constructor. We have a destructor. Remember, a destructor is a method that's called the instant an object falls out of scope. We'll talk more about the destructor in a minute. We'll have a method to insert an item. So here we're gonna pass a constant reference of type T. Right, this is the generic type. So we basically want to pass by reference, but we know for sure we shouldn't be changing elements inside the insert function. That's why I make it constant. And then in order to traverse through the list, we need some way to control a loop. And that's what first and next are going to be used for. We'll cover those in a little more detail in a second. And then we'll have a method to get the length, the number of elements that are in the linked list, and an isEmpty, which returns true or false whether there are any items in the list or not. Okay, so what data do we need? This is the public interface. These are the methods. Okay, if we look at the data, okay, we'll see that we declare this thing called a node. So we have the struct that's sitting inside of a class. Again, remember, a struct is really just it's a cookie cutter. We're defining what a node is. So a node is a piece of data, type T, that's the generic type, and a node pointer called plink. So this might look a little odd. We're declaring this thing called node, and inside the declaration of the type, we're saying this is going to be a node pointer. This is actually perfectly legal in C++, and it corresponds exactly to the picture I drew, where we have a node being a piece of data and a link to the next node. Okay, so this is a cookie cutter. We don't actually create a node here. This is just defining what a node is. Okay, the actual pieces of data that the linked list is going to have, we're going to have a node pointer called I'm going to call it phead. Okay, and this is always going to point to the first node. We're going to have a current pointer. This is going to be useful to us when we're traversing through the list. pCurrent is always going to point to the current element that's being processed, and then we'll move current to the next node. And then number of elements will be the number of elements that are being stored inside the list. Okay, so if these are really our only three pieces of data, then we have to think, well, how are we going to initialize a linked list? Remember, we initialize all of our data in a constructor. So this is a templated constructor for the myLinkedList class. And the way we're going to start, we're going to create this linked list is it's going to be empty. So phead and pCurrent, these are node pointers. We're going to set them equal to null, meaning they don't point to anything. And we're going to say that the number of elements inside the list is 0. Okay, next we have to think about, well, how are we going to insert into a list? Okay, and I'm going to break this into kind of two problems. First, let's think about, well, how do we insert into an empty linked list? And then we'll talk about how do we insert into some non-empty linked list. Okay, so there's some steps here. Remember, we start with this pointer called phead, which points to nothing. Phead is a null pointer. Okay. So if we want to insert into a empty list like we have here, the first thing we're going to do is create a new node on the heap. So we can use maybe some pointer to create a new node. Remember, node has a piece of data and a link. Okay, step 2 is we're going to fill the new node's data. Okay, so remember the interface to insert is we're going to pass in something that we want to add to the linked list. Okay, so whenever we do an insert, we're going to set the data portion. That's the second step. Third step, we're going to set the link of the new node to be whatever the head points to. So we'll set the new node's link to be whatever the head points to. Okay, which right now the head points to nothing. It's a null pointer. Okay, so here's the new node. Its link. We're also going to make a null pointer. It should have a value of 0. Step 4 says we're going to set the head to point to the new node. We're going to move the head pointer to point to this new node. Okay, so p head right now points to the null pointer. Instead of doing that, we're going to make it point here. Okay, so if I kind of stretch this out and clean it up a little, what we're going to end up with is p head points to this new node, where the new node's link is null and the piece of data is whatever we passed into insert. Okay, and then step 5, we're just going to increase the number of elements by 1. Because we're adding a new node. Okay, so now the question is, this is how we insert into an empty list. Notice it went from empty to having 1 item in it. Well, now, how do we insert into a non-empty list? So let me draw the picture again. Okay, this is now a non-empty list. P head points to the first node. First node's link is null. Turns out that we can follow the exact same steps to insert into a non-empty list. Okay, so the first step says we're going to create a new node on the heap. Okay, it's totally empty right now. We're going to fill in the new node's data. Let's say we're going to put the value y in there. We're going to set the new node's link to be whatever the head points to. Right now the head points to this node. So we're going to have this new node's link also point there. Step 4, we're going to set the head to point to the new node. So instead of head pointing to the one with x, it's going to point to the one with y. And then we're going to increase the number of elements from 1 to 2. If I kind of clean this up, we will have a linked list that looks like this. And again, if I were, let me just do one more insert. And again, I'll follow the exact same steps. Okay, so if I were going to insert the value z, first thing we would do is create a new node on the heap. We'd fill the data section of the new node. We'll set the new node's link to be whatever the head points to. Right now the head points to the node with the y in it. And then we're going to set the head to point to the new node. Instead of it pointing to y, it's going to point here. And we're going to increase the number of elements. If I stretch this out, we'll see we have a linked list that looks like this. Okay, so let's look at the code. Okay, we've seen the picture. Now the code is pretty straightforward, although the syntax is going to look a little strange first, but try and keep that picture I just drew in your head as we go over this. So there were these 5 steps. Somebody's going to call insert and pass in a value that they want to add to the linked list. The first thing I do is create a temporary pointer, a node pointer, and I assign it the value of saying new node. That means go to the heap and make room for a node, and we're going to return the address of that node to be stored inside ptemp. Step 2 is to fill the data. So since we have a pointer to a node, which is it's not a simple type, it's a complex type, we're going to use our arrow notation, and we're going to say ptemp's data is equal to the parameter that gets passed in. Okay. Step 3 says we're going to set the new node's link to point to whatever the head points to. So ptemp and phead, those are both node pointers. They both hold the address of nodes. So ptemp's plink equal to phead means go to the new node, whatever node we're creating, and the link is going to be equal to the address that's stored inside the head. You know, both head and link hold the address of something. And then step 4, we're going to set the head to point to the new node. So again, phead and ptemp are both node pointers. They hold addresses. So when I say phead is equal to ptemp, that just says phead now points to the new node. And then lastly, we're going to increase the number of elements by 1 to indicate that we're adding a new item. Okay, so that is not a lot of code, but it's a pretty dense amount of code. It's going to take you a little while to wrap your head around this. But I suggest you draw the picture yourself and kind of prove to yourself that really will add items in this linked list. Okay, so next we have to think, well, how do we traverse the list? Right? The reason why we have containers is so that we can march through them and do something with each piece of data in them. We don't have array access anymore because the elements are not next to each other in memory. We don't have that random access. Okay, so what we want to be able to do is control some kind of loop, and that's exactly what first and next do. They're going to return a true and a false value that are going to be used to control a loop. And first will return true if there's at least one item in the list, and it will also fill in this parameter that gets passed in with the value at the head of the list, okay, the first item. Next will also return true if we're not at the last element in the list, and it will also assign the parameter to the current pointer's data. So let me jump ahead for a second here and look at a main method that uses this linked list. So this is going to be a linked list of floats called float list, and we're going to insert a bunch of items. Okay. And now when we want to iterate through them, we always iterate with this combination of calls to first and next. So starting with this local variable called val, okay, we're going to say float list.first, and we're going to pass in val. And as long as there's at least one item in the list, this should return true. And as a side effect, val is going to hold the piece of data that's in the head node. Right? We're gonna right now it's kind of garbage value. We're going to pass it in by reference, and it's going to be set equal to the first piece of data, whatever the head points to. So then we can do something with it. I'm just going to print it out here, and we will have processed the first element. Now to process all the other elements, we're going to call next. So floatlist.next. Again, we're going to pass in val. This whole function will return true as long as there's more items to process. And as a side effect, we're going to fill in val with the next item in the list. So here we can process it or do something with it, and then go back and grab the next item. And this will return true as long as there's more things to process. Okay? And once we finally get to the end, when there are no more, next will return false, and we will fall out of this code. Okay, so let's go back to and take a look at first and last. So again, first takes in a t reference called elem, And the idea here is we're going to return true if there's at least one item in the list, false if the list is empty. So here we're just checking, is the list not empty? If the list is not empty, the flow of control will get inside here. We'll set the return value to true, and then we'll set the reference parameter equal to the piece of data at the head. That's always the first node's data. And then here's where we're going to start to use pCurrent. That was that second node pointer. And pCurrent, the idea is it's always going to point to the next item to process. Okay, so pCurrent is going to point here, and then after we call next, it's going to point here. And after we call next again, it's going to point here. And after we call next again, that's when there is nowhere to go, and the next function should return false at that point. Okay, so we just kind of get things started by setting pCurrent equal to pHead, so both of those pointers point to the very first element. And then we just return whatever's in the return value, so that it's either true or false. If it was true, then elem was set, and we can use whatever argument got passed into the first function. We could use that in main. Now, the next function looks very similar. Again, we're going to return either a true or false. True if there's more items to process, false if we're at the very end. Okay, and what we're going to do here is we're going to check to see, is pCurrent's link not equal to the null pointer? So again, let's look at the picture. pCurrent is, let's say it was pointing here. Well, the link is not null. It actually holds the address of this node here. And if pCurrent happened to be pointing here, its link is also not null. It holds the address of this one here. But when pCurrent is pointing here, pCurrent's link is null, and that's when we know that we can stop processing items in the call to next. So as long as pCurrent's link is not equal to null, what we will do is we'll move the pCurrent pointer forward one element. Okay, so this is an assignment statement. We're trying to set a new value to this pointer called pCurrent. And the value we're going to set it to is pCurrent's link. So if pCurrent is pointing to the first item, pCurrent's link will hold the address of the second item. So we're taking the address of the second item and we're storing it inside pCurrent. And that has the effect of basically moving pCurrent from pointing to this item. Okay, we're taking pCurrent's link as the address of this one, and we're storing that back inside pCurrent. So it no longer points here, it does point here. Okay. Then we're going to indicate that, yes, there were more items to process, and then we're going to grab the piece of data that pCurrent now points to a new node. We're going to grab pCurrent's data and store that in the pass by reference element. Okay. And then finally we're going to return either, again, a true or false. Okay, so again, I suggest you really take a close look at first and next and how we're using it here in the driver. Basically, first and next, it's a way to control a loop where we want to be able to get the value in each one of the nodes. And the way we do this is we start with the first one, and then for each additional item, we are going to be able to process it like this. Okay, we have a couple other kind of smaller functions. Length, that will just return the number of elements. Is empty, that'll just say, is the length exactly equal to 0? If that's true, it's empty. If this is not true, if the length is greater than 0, then obviously the linked list is not empty. Okay, lastly, we have to think about how are we going to return memory after we're done with it. Right? So if we're allocating nodes on the heap, at some point we have to deallocate them. We have to free the nodes that were created on the heap when the linked list falls out of scope. So what it means to fall out of scope, right? This linked list was declared here in main. So when we come to the ending curly brace of main, that's when a special method called a destructor is called. So every object has a destructor, and it will be implicitly called whenever an object falls out of scope. So we never call destructors explicitly, we the programmer. They're always called implicitly for us when an object is no longer being used. Okay. And that's actually a perfect time to go and deallocate all the nodes that we allocated on the linked list. Okay, so let me show you what's going to happen in the destructor. So we're going to have this linked list. Have a series of nodes that were created on the heap. Okay, p head points to the first one. The last one has a null pointer. Okay, now since we created each one of these on the heap, we, the programmer, have to deallocate it. So I think what we're going to do is we're just going to start with the first item, and we're going to delete it. Okay, but then what we want to do is we want to update the head so that it points to the next item in the list. Okay, and then we're going to basically repeat the process. We're going to delete that, and then adjust the head pointer to point to the next one. We'll delete that one. Go to the next one. We'll delete that one. And as soon as the head is set equal to the null pointer, that's when we know we'll have deleted all the elements. Okay, so this is the destructor. Remember, destructors, they're always the same name as the class, but they start with this tilde. I create this temporary node pointer called ptemp, and I say as long as the list is not empty, I set ptemp equal to phead. That means ptemp is going to point to the first item. And then I'm going to set phead equal to phead's link. This is going to bypass, this is going to make the head point to the next, or the second item. Then I'm going to, I do a little bit of a debug here. I'm just going to print out that I'm deleting this piece of data. Then I delete ptemp. Okay, and that's okay because remember we already moved phead to move just beyond ptemp. And then I'm going to decrease the number of elements, and then I'm going to go back to the top here, and as long as the list is not empty, we'll use ptemp to point to the head, which will now be the second node in the list. We'll move phead to the third node in the list because phead's link is the address of the next one. And then we'll delete ptemp, decrease the number of elements, and increase. And here that's exactly what the picture I drew here is. We got rid of the first one, then the second one, then the third one, then the fourth one. And eventually when there are no more items in the list, well, that's when we're done with the destruction of this object. Okay, lastly, I'll just show you that main function again. Okay, so we create a linked list of floats. We check to see is it empty. At this point it should be empty. Then we do a series of inserts. I just happen to insert the numbers in order. Should tell me exactly how many items there are. And now I want to traverse. I want to print out all the values that are in this linked list. So I have this empty float called val, and I'm going to call first. This will return true as long as there's at least one item in the list, and val will get set. Val will hold the first piece of data. I can see out val, and then as long as there are more items, each iteration, each time I call next, val is going to hold a new item, and only when we get to the very end of the linked list will next return false, and when that happens the flow of control will fall out here. And when we come to the end of main, okay, that's when the linked list falls out of scope. That's when the destructor will be implicitly called. Okay, so let's kind of analyze what a linked list is. Okay, so inserting nodes dynamically in a linked list is more regular and consistent than inserting items in a safe array. This is because every once in a while, when someone adds to a safe array and it's full, it needs to be resized. And this resizing, which involves copying all the elements over, can take a long time. With the linked list, there are no exceptionally long delays when inserting an item. It takes about the same amount of time to insert all these items in a linked list. Whereas with the safe array, every once in a while, it takes a really long time to do an insert. So that's why I say inserting into a linked list is more regular and consistent. The amount of time it takes to search an unordered linked list is about the same as an unordered safe array. So in both cases, you just kind of have to start at the beginning. Remember, these are not sorted. And you just have to kind of move through from the first to the last and see if what you're looking for is there. Although if the collections were sorted, you can use a binary search on a safe array, but you cannot on a linked list. The binary search relies on you having random access, and you only get that with an array or an array-based container. Some other differences between a safe array and a linked list. A linked list, like I said, does not have random access to the elements. So what that means is it's a big O of n operation to access any piece of data in the linked list, because you have to, like I said, start at the beginning and follow the links until you either get to the desired position or you get to the end. Whereas a safe array, you do have random access. The physical way that memory works is it takes the same amount of time to access the first element as it does the last. The linked list is more memory efficient. Okay, so we only allocate room for what we use. The safe array is relatively memory inefficient because we're always allocating room for items that may actually not ever be used. So remember our doubling strategy. When the safe array gets filled, we double the size of the array and we copy all the elements over. So the linked list is memory efficient but processor inefficient. It's processor inefficient because it's a big O of n operation to go access any element. And the safe array is processor efficient because we have random access, but it's relatively memory inefficient because we always make the array bigger than we actually need. Right? Now, you might think, well, we can make the safe array memory efficient by only allocating room for one new item when it becomes full. Okay, so if we push to the back of a safe array, instead of doubling the size, what if we just made a copy of the array, but we made it just one item bigger? Okay. Well, that would make the safe array memory efficient, but then it would become very processor inefficient, because every time we do a pushback now, we'd have to copy the entire array over, and that takes a tremendous amount of time. So safe arrays and vectors and all array-based containers, they're always implemented with this doubling strategy so that we can minimize the number of times that we actually have to do the copying. But the doubling strategy, of course, means that we're basically being fairly memory inefficient. So the one takeaway that you should have with these linked lists, they're very memory efficient but processor inefficient, whereas safe arrays are very processor efficient but memory inefficient. So you might want to use a safe array when you have a lot of memory, but maybe not necessarily a very fast processor. And you'd want to use a linked list when you have maybe not a lot of memory, but you have a lot of CPU cycles to spend. Okay, so we're going to talk about the differences between all these containers, and these differences are going to be important. When you're writing a program and you have to decide, well, what type of container should I use, you'll have to know kind of the pros and cons of each one of the container types.